Assalamualaikum warahmatullahi wabarakatuh. I back to Dr. Hidayah. So today me and my team are going to present about theory of thermodynamics in a real life application. So the device that we choose is iron. Before we start, let me introduce my team. I am the speaker, Aina Mazliyana, with my two members, RABIATUL and QISTINA. Let's start with the introduction. A closed iron is a small appliance that we use when heated by place it on the clothes to remove wrinkles and unwanted creases. Domestic iron generally range in operating temperature from between 121 degrees Celsius to 182 degrees Celsius. It is named for the metal iron of which the device was historically made. Iron works by loosening the ties between the long chains of molecules that exist in the polymer fiber material with the heat and the weight of the ironing plates. The fiber are stretched and the fabric maintains its new shape when cold. Some materials, such as cotton, require to use water to loosen the intermolecular bond. Next, how does the iron work? So first, an electric current is passed upon the principle of heating effect of current. This principle states that when an electric current is passed through a conductor, it generates heat because of the resistance present in it. Second, the resistance converts electrical energy into heat energy. The formula for the heat produced due to resistance and current. Third, this principle has many applications like heater, electric iron, and etc. In these types of device, they generally have a coil whose resistance is much higher, which in turn converts electricity into heat energy. Fourth, the other given option does not have any role in this type of applications, where heating is required. The heat produced also depends on the voltage applied across the applicants. Fifth, more the current passed through, more the heat will generate. A good conductor of electricity does not show in this property. The materials having high resistance can only show a heat effect. Next, different types of iron. We have steam iron, handle garment steamer, and also basic iron.
The process involved in iron is first the conversion to steel, basic oxygen furnace process. Oxygen blowing is oxygen blown through the molten iron to oxidize the impurities. The thermodynamics principle is these oxidation reactions are isothermic, which is releasing heat and lowering the impurity level. This is the diagram of basic oxygen steel making. The second process involved in iron is the extraction of iron from ore, blast furnace process. The chemical reaction, iron ore is reduced by carbon monoxide in the blast furnace. The heat source is combustion of coke generates the necessary heat. The thermodynamic principle for the extraction of iron from ore is the reduction reaction is endothermic and needs heat input to proceed. The diagram shows the blast furnace process. The third process involved is heat treatment, which is annealing, quenching, and tempering. The temperature control, iron is heated and cooled to alter its microstructure. The phase changes, different iron phases like ferrite and austenite are formed based on the temperature. The thermodynamic principle is these oxidation reactions are exothermic, which is releasing heat and lowering impurity level. Carnot cycle is the thermodynamic cycle analysis for iron. First, the isothermal expansion A to B. The working substance, which is iron, absorb heat QH from a hot reservoir at temperature TH and expand isothermally. During this process, the temperature remains constant and the iron does work on the surrounding. The heat absorbed QH can be calculated using QH equal to nRTH ln VB over VA, where N is the number of moles of iron, R is the universal gas constant, VA and VB are the initial and final volumes during the isothermal expansion. Secondly, the adiabatic expansion B to C. The ion continues to expand but no heat is exchanged with the surrounding. The temperature of the ion decreases from TH to TL. The relationship between temperatures and volume is given by TH VB to the power of gamma minus 1 is equal to TL VC to the power of gamma minus 1, where gamma is equal to Cp over Cv is an adiabatic index for ion. Cp is the specific heat capacity at a constant pressure and Cv is the specific heat capacity at constant volume. Thirdly is the isothermic compression, C to D. The working substance, which is iron, release heat QL to a cold reservoir at temperature TL and compress isothermally. The temperature remains constant and the work is done on the iron. The heat release QL can be calculated using the equation is QL is equal to N RTL ln VD over VC. And lastly, from the Carnot cycle, which is the adiabatic compression D to A. The iron is compressed adiabatically and no heat is exchanged with the surrounding. The temperature of the iron increases from TL to TH. The relationship between the temperatures and the volume is given by TL VD to the power of gamma minus 1 is equal to TH VA to the power of gamma minus 1.
Next, let's see law of thermodynamics that involve in the ion. So, an ion is a practical application of thermodynamic principles. It involves the first and second law of thermodynamics. This is because the process satisfies the first law of thermodynamics to proceed the second law of thermodynamics. So, according to this law, heat is not completely converted into work. The kinetic energy cannot be transferred into potential energy. And last, heat flow from cold to hot is very impossible. So, let me explain how the first law involved in the ion. So, when the ion is plugged in, electrical energy from the power source is transferred to the heating element inside the ion core. The energy then will be converted into thermal energy, which is heat, as it will be used to increase the temperature of the ion's plate. And the equation used, Q equal to U plus W, can be used to calculate the amount of heat generated during the process. Next, the second law involvement. So, this law will dictate the heat energy to flows from a hotter object to colder object. When the hot plate of the iron is applied to the clothes, heat will transfer the iron to the fabric, which is from high temperature to low temperature. This process will continue until thermal energy reach its equilibrium. So, this transfer of heat causes the fibers in the fabric to relax and smooth out wrinkles. So, let's talk about the efficiency and performance of the ion. In thermodynamics, the thermal efficiency is the dimensionless performance measure of a device that uses thermal energy, which is the case now is thermal efficiency used by ion. We can use the formula of thermal efficiency to calculate the ion performances and its efficiency, which is the formula thermal efficiency equal to net work output over total heat input. From this calculation, the power consumption of an electric clothes iron, like any electrical appliance, will depend on the following primary factors. First one, the wattage of electric iron. The wattage essentially indicates the rate at which the iron consumes electricity. Electric clothes irons generally have a wattage ranging between 500 until 2000 watts. The second, the electricity tariff in one's locality. This refers to the cost per unit of electricity charged by the provider. We can simply multiply the wattage with the cost per unit to find out the iron's power consumption cost. So, for the operational hours, the more you use the iron, the higher the power consumption is. So, from the law of the thermodynamics, we can have a suggestion for the improvement of the iron. First, we can enhance heating element efficiency by develop heating elements made from materials with higher electrical to thermal energy conversion efficiency. For instance, using advanced ceramics or composite materials can increase efficiency and reduce energy loss. Iron also can be improved by insulate the heating element better to minimize heat loss to the surrounding and ensure more energy is directed to the iron plant. Second, thermal management system. By implementing heat recovery system that capture waste heat from the iron and reuse it for maintaining plant temperature or preheating water for steam generation, we also can design the plant with independent heating zone that can be controlled separately. This allows the iron to apply more heat where needed and reduce it in other areas, while optimizing overall energy use. As a conclusion, incorporating the principle of the first and second laws of thermodynamics in the design and operation of clothing irons results in devices that are more energy efficient, effective, and user-friendly. This enhancement not only improves the ironing experience but also contribute to a more sustainable and environmentally friendly approach to household appliance. By continuously innovating and applying this thermodynamic principle, we can create clothing irons that meet the demands of modern user while adhering to the highest standards of efficiency and performance. So, the focus on improved heating element efficiency, smart controls, advanced material, and innovative thermal management system will ensure that the iron operates within the bounds of energy conservation and optimal heat transfer. This enhancement lead to an iron that is not only better for the user but also more environmentally friendly, aligning with modern needs for sustainability and efficiency. Thank you.